Hello friends, welcome back to our channel ST In this video we will see how to interface serial flash. So basically we have this Atmel 25F4096 memory IC, and it is of 524288 bytes. Okay, it consists of 256 page size. Okay, and the sector size is 65536. So basically if we calculate like how many MBs this chip can store, right? So 524288, right? 524288 divided by okay, 1024, right? So it is 512 KB, 512 KB. This is bytes, right? 512 KB, yes. And this 512 KB. So this memory IC can store up to 512 KB kilobytes of data. So if you can see the specifications of this IC, right? 8025F4096. So this IC can store up to 4 megabits. Okay, this is 4 megabits, right? 524288 into 8. So like one byte is equals to 8 bits, 8 bits of data. So that becomes 512 KB, right? Now we will see, right? The page size is of 256 and sector size is of 65536. So we will go over here, we will check the page size, right? So this is page size, page size, page size. We will check the page size. Okay, so I have highlighted few points on the data sheet. I have highlighted few points on the data sheet, so we will see all those points one by one. All this sector erase and all this, we'll see all these sector erase, write enable operation and everything. Yes, so byte mode 256 byte page mode. Okay, so if we calculate 256 bytes page, okay, and 65536 sector size, it must be overwritten here somewhere here. Yeah, that's, let's, so it must be written over somewhere here. Okay, so I'll highlight this page mode, select, highlight 8 sectors of 64 KB. Yes, so sector architecture 256 pages per sector. Okay, so 64 KB, 65536 bytes is equals to 64 KB. Okay, so each sector consists of 64 KB and the 256 byte in each page. Okay, so now first we will see like what our simulation can do, what data that we are writing. Okay, I'll just give you a glimpse what our programming is doing in the main code. Okay, so first thing is we have started with chip erase, then we have started with write memory data. Okay, and then write status register, read status register. So for now what we will do is we will disable this section and we will enable this section. Okay, so we will erase the sector, then we will write the data again. Okay, so we will build this code. Okay, we will build this code. As you can see, we have this write data. Write data consists of several lengths of several bytes. So write data is an uint 8-bit array which consists some data. Some data is that this is the random data. Okay, so we are writing that write data array into the memory. Okay, I'll go to SPI Flash, SPI init. Have I written SPI init? No. Okay, So like first we will check whether our code is working or not. So second thing, I'll get you through the pin configurations, which pins are used for SPI communication, okay, then how these pins are used, how these pins are configured, which pins are configured as input pins, which pins are configured as output pins. We'll see the clock transition over here, sorry, we will see the data transition over here with respect to clock, and whatever data we have read we will pass it on the UART, okay. So for this simulation we have used STM32F103C8, which is a blue pill board. Now we will load this, okay. So as you can see, the hex file that is created, it is matching with 8th November. So the hex file that we have created is of 8th November 9:44 PM. We'll load this, we'll click on OK. Yes. So now we can see, right, this is the SPA memory. From location 0000 we have erased the data, okay. Now we'll again load. So to erase the chip fully, some delay is needed after the instruction. So now you can see that the data is being written. So you can see the clock cycles, we can see the chip select pin, and we can see the data that is being transferred to the slave device, that is SPI memory device, that is the memory device, okay. Now for this moment we are not reading back any data, so we are not getting any transition on the SO line. There are SI line and SO lines, okay. So as we can see that the data is being written properly, that 64 bytes of AA is written over here, BBCC, and again we can see, we can stop, right, again we can see that it is, the sector is erased, okay. So sector is erased, and we can see the data, right. So this is a demonstration that our simulation is working perfectly fine, okay. Now we will go into the code. We'll see, first we will see the pin configuration. So for our simulation, which pins are used as input pins, which pins are used as output pins. So for SPI communication, right, so for SPI communication we need few pins, right, that is, first one is chip select. CS pin and SS pins are the negative pin, CS pin or SS pin, these are the negative working pins. That means to enable the device working, we have to write 0, that is we have to pull this pin 0, so we have to pull this pin as low to enable the device working, okay, to operate the device. So as you can see, SS, okay, in our simulation we have connected CS or SS pin to a PA3, okay. Now as we can see, PA3 is an output pin, okay. We'll see in GPIO core, PA3, it is a output push pull pin, it is connected to pull up, and the maximum output speed is high, okay. Now we'll go over here, clock pin. So this is the output pin from microcontroller. So PA0, right, PA0, it is again output pin, okay. Output level is low, GPIO mode is output push pull, GPIO is pull up, and maximum is high, okay. Now like we have to take care for this clock pin, okay. So this GPIO output level should be low. I'll explain why this setting has to be done. Okay, now we'll go to PA1. PA1 is GPIO output. PA1 is GPIO output that is connected to SI, right? So slave in, that means master out, slave in. MOSI pin, that is MOSI pin. Okay, so here we can see that GPIO output level is low, GPIO mode is output push pull up is connected, and maximum speed is set to high. Now PA2, this is MISO, that is master in, slave out, that is input to the master, input to the controller. So here input mode, no pull up or no pull down. Okay, now along with this we have also configured with several pins, like UART pins we have configured. Connectivity, UART pin asynchronous 9600 baud rate. Okay, then we'll go to the system core, RCC, ceramic, high crystal. Okay, ceramic and PC13, that is connected to the LED. So this is again output pin. We'll go to the settings, PC13, GPIO output level low, GPIO mode output pull up is connected, and maximum speed is set to high. Okay, now we'll go to over the clock configuration. So we are using the RC crystal. Okay, that is the internal clock generator. We are using this internal clock source. So for this simulation we are using the RC, that is internal clock. Okay, so internal clock is given to the PLL source. Okay, now these settings have been done. Now we are like internal clock is of 8 megahertz, so divided by 2 is 4 in, like we get the 4 to the clock input. Now that is multiplied by 9, so 4 into 9 is 36. So and the system clock source is set to the PLL clock output. Okay, so we are giving the 36 megahertz of clock to our all peripherals except PB1 peripheral clocks. Okay, now we will go to generate code. So these are the basic settings that have been enabled. Now we will go to in our controller simulation. Okay, we'll go to edit properties. So oscillator frequency is of 0 megahertz because we are using the internal clock frequency. Clock scale is off. OSC 32 frequency is also set to 0 megahertz. Okay, now we'll cancel this. We'll go design. We'll go to the configure power rails. Ground is connected to ground and VSS. Voltage is 0. VCC is 3.3. VCC and VDD, and VEE is set to 0. Okay, we have to set it, click it as OK. Now these are the controller settings and the pin settings. Now we can see that the write, protect and hold pins have been pulled to high. Okay, so these pins are working as low. So if we connect it to the ground, this write, protect will be enabled. So for our operation or for our simulation, currently we don't need the write, protect or hold operation, so we have tied them to the VCC. Okay, power. Only on these 4 pins we will be operating, so we kept these 2 pins on VCC. Okay, now we have connected one red LED. We'll check its property. It is analog, set to 2.2 volt, and drive current will be 10 milliampere. Okay, now we will go into our code. Okay, we can see the chip erase, write memory data, sector erase, HAL, write memory data. Okay, so for this video I wanted to cover the SPI communications. What are the SPI modes? The device SPI mode, like the flash device SPI mode, then the device data sheet, how many bits are there, its true meaning, what is the true meaning of it, the write cycle. Okay, the chip erase operation, that is, this is the write operation, basically write operation. Okay, then this is the chip erase operation, how it is explained in the datasheet, and how we have written the code according to the explanation as per the datasheet. Okay, so does our code matches with the explanation of the datasheet? That we will see. Okay, then sector erase operation, this is time or yes, both we will see. Okay, then device ID write operation. Okay, okay, so I'll remove this write operation, basically write cycle write operation. Sector erase operation we will see. Okay, then write enable instruction and sector protect. Okay, so to start with SPI communication, so serial peripheral interface. Okay, this is the SPI communication. This can be full duplex or half duplex, because these have two separate lines for data out and data in. So master communicates with the slave device using 3 pins, mainly clock, serial in and serial out. So master out slave in, that is MOSI pin, master in slave out, that is MISO pin. And there is another pins like chip select or slave select, then there is write protect, and then there is hold. So these 3 pins are what we can say additional pins, as we have seen that we are using the push pull transistor, right? So push pull, so main advantage of SPI communication, that is it operates in push pull mode. Okay, push pull transistor mode. So the operation is faster as compared to open drain. Second thing is we can connect as many devices as possible, so there is no limitations. So the disadvantage is like, as we go on increasing the slave devices, the number of chip selects pins will also go on increasing, so that will limit our other peripheral interface. Okay, so that is one limitation for this SPI communication. But we can go for the higher speed also, so that is not the issue. Sometimes chip erase operation takes more than few seconds, so that we need to take care. Okay, that is one thing. So this is serial peripheral interface. I'll share you few links. Like why SPI communication, like what is the difference between the SPI and I2C. As you can see, I have these pins. Okay, so this is serial data is sent 1 bit by bit at a time, and that's why it is called as serial communication. Okay. Now what I wanted to tell you, like in every SPI communication, like there will be a controller, that is a master, and there will be a slave. Okay, so master and slave communication will be done using 4 lines, 4 pins: slave select, then clock, MOSI, master out slave in, and MISO, master in slave out. Okay, so these 3 pins are configured as an output pins, and the MISO pin, that is slave out, that is configured as input pin at the master side, that is the controller side. So as we have seen, only this pin, that is PA2, is configured as GPIO input pin. Rest of the pins are configured as a GPIO output pins. Okay, now we can see like everything is explained in this PDF, and I'll share you the link. Okay, now second point, that is SPI modes. So there are 4 modes of SPI communication depending on the clock polarity and clock phase. Okay, so we will check. There are 4 modes of SPI communication. Okay, mode 0, mode 1, mode 2, and mode 3. So clock polarity and clock phase, that is considered as SPI mode 0, and clock is 1 and clock phase is 1. Clock polarity is 1, clock phase is 1, that is considered as mode 3. So you won't see that there are certain bits that we can configure for this. Okay, so basically what this clock polarity and clock phase means, right? So first thing I'll explain what is the clock polarity. The clock polarity means, like, while SPI is starting, right, the state of the clock pin, either it is 0 or 1. Okay, the starting polarity, that is considered as a clock polarity. So if we are using SPI mode 0, right, the clock polarity is 0. What it means is, basically whenever SPI communication is start, the clock must be low. Okay, that is one thing. Now what is clock polarity is high? When clock SPOL is 1, it means when SPI communication is starting, the clock polarity must be set to high. It should be high. When the CS pin goes low, the clock should be high. Okay, now we'll go for the phase, right? Phase, like 0 and 1, there are only two states. So phase 0, it means data is sampled at rising edge and buffered at or shifted in the buffer on the falling edge. So 0 means, like, data is sampled on first edge. Okay, so whichever the first edge that occurred, there the data will be sampled and shifted on the second edge. Okay, like, we can see that data is shifted out, data is sampled on the falling edge and shifted out on the rising edge. Okay, so here data will be sampled, but keep in mind, okay, for SPI mode 1, where the clock polarity is 0, clock phase is 1. Okay, data is sampled on the falling edge and shifted out on the rising edge. Where in the SPI mode 0, we can see when the clock polarity and clock phase both are 0, data is sampled on the rising edge and shifted out on the falling edge. Okay, so these are the, depending on the clock polarity and clock phase. Okay, I won't go on explaining SPI mode 2 and mode 3. Okay, just remember that is clock polarity. When the clock polarity is 0, right, it means when the chip select is there is transition on the chip select, that is, it is getting low, or whenever we are enabling the device operation, the clock polarity should be 0. Okay, and whenever SPOL is 1, it means whenever we are enabling the device operation, the clock must be set to high. Okay, then clock phase, when the clock phase is set to 0, it means data is sampled on the first edge. Okay, it may be rising edge or it may be a falling edge, depending on the clock polarity. Okay, so when CPH 0, it means data is sampled on the first edge, first transition on the clock. Okay, then data is shifted out on the second edge. When clock phase is 1, okay, when the clock phase is 1, data is sampled on the falling on the second edge and shifted out on the first edge. Okay, so that is, like, that is the working for, that is the SPI mode. Okay, so I won't go that much deep into the SPI modes as of now. So these are the points that we have to consider while writing our SPI code. Okay, now device SPI mode. So I have explained you the four modes, right? SPI mode 0, 1, 2 and 3. Okay, so depending on the clock polarity and clock phase, we can select the SPI modes. Now we need to check, like, the device that we are using, so it is compatible to which SPI modes. Okay, so you can see datasheet describes the mode 0 operation. Okay, and the supports SPI mode 0 and 1. What it means is clock is 0, right, phase is 0, either clock is 1 and phase is 1. Okay, so this device does not support SPI mode 1 and 2. Okay, so basically we will go with the SPI mode 0, because like, as the datasheet is described with the mode 0 operation. Okay, now that is, so SPI mode 0. Okay, now device datasheet, we will go how many bits are there, so how many bits that we can write into our device. So as you can see that we have 4 megabits. Okay, 4 megabits, that is 419430 bits. These many number of bits that we can write into this IC. Okay, but these are the bits, not the byte. So if we divide this 419430 4194304 bytes with 8, right? Because like 8 bits constitute 1 byte of data, or 1 byte of data is equals to 8 bits. So it is 524288. So we can see that we can configure 524288 words of 8 bits, right? One word is of 8 bit, that is a 1 byte, right? So like we can configure these many number of bytes of data, 524288. So if you want to divide it, or if you want to check how many bytes actually we can write in kilobytes, right? So we can write 512 kilobytes of data. So we can save 512 kilobytes of data into this flash IC. Okay, now we will go. So this is enabled through chip select pin. Okay, and accessed via 3-wire interface consisting of serial data input SI, serial data output SO, and serial clock. Okay, now block write protect means sector protect or block protect. It constitute of 1 by 8, 1 by 4, 1 by 2, or entire memory. So basically there are 4 block protect operations that we can constitute. Okay, so either we can block protect the entire memory, or first half of the memory, or first fourth of memory, or first 1/8 of memory. Okay, so that we can protect by setting these bits, block protect bits. Okay, now hardware protection is provided via write protect pin. So whenever this write protect pin is tied to low, tied to ground, the write protect will be enabled, and we won't be able to write any data into the device. We can read the data, that is fine, but we won't be able to write the data. Okay, we won't be able to write the data. So yes, now the most significant bit, now we will go like how the data transfer takes place. The MSB is sent first, transmitted first, and received first. Okay, so this is again one thing that we need to consider. The MSB is sent first and received first. Okay, now serial, there are some few opcodes to interface with the device, right? So whenever chip select is low, okay, though device is selected whenever chip select is low. Okay, so this can be like this can be the operation, like whenever we want to access multiple device, we can use the same IC with multiple chip select pins. Okay, not the same IC, same type of IC with the multiple chip select pins, and we can interface multiple same ICs over here, or the same SPI 3 lines, that is SI, SO, and clock, but with different chip select pins. Okay, so we'll go over here. Like like this we can interface multiple same ICs, multiple slave ICs. Okay, so as you can see that there are multiple chip select pins, multiple slave select or chip select pins. Okay, but the clock, SO, and SI pins, these 3 pins are common. Okay, so like how many bits? 4 megabits we can interface, right? 4 megabits we can interface, that is 512 kilobytes of data that we can store. Okay, now we will go over the write cycle, chip erase. Okay, so all instruction addresses data are transferred with MSB first. So yes, there is an instruction set for interfacing with this 825425F4096 IC. So this is the opcodes that we need to send to this instruction basically. Okay, so write enable, we have to send it as 0x00, then this is don't care 110. So if we can consider it x as a 0, basically x means it can be 0 or it can be 1, so we will consider 0. So 0x 0000 0100, sorry 0110. So this will be 0, this will be 6, right? So 06. So sending 06 to the device, it will indicate that we have sent the write enable instruction. Okay, now this is reset write enable latch. Okay, so WRDI, reset write enable latch. So for this 04, read status, for read status register 05, for write status register 02, sorry 01, for read the data from memory array, that is 03, to program the memory array or to write, this is basically program means write, we have to send is 02. Sector erase, for sector erase 52. Okay, for chip erase 62, and read device manufacturing ID is 15. Okay, so we'll go with one by one instruction, that is write enable instruction first, that is write enable. Okay, device will power up in the write disable state when VCC is applied. Okay, so all instructions must therefore be preceded by write instruction, write enable instruction. So whenever we apply the power to the device will be in the write disable state. Okay, to bring it into the write enable state, we have to send the write enable instruction. So before any instruction, we have to set the write enable instruction. So we have to send this opcode, that is 06, that we need to consider. So we will mention it over here as before sending any instruction, we need to send write enable, that is write enable NSTR instruction. Okay, so write enable instruction set 0x06. Okay, this is the opcode for write enable. Now write disable, to protect the device against the inadvertent writes. Okay, that is write disable instruction, we have to write the write disable instruction. So it is independent of the state of the W pin, that whenever we are sending the write disable instruction, independent of or irrespective of the W pin, whether W pin is connected to VCC or ground, we can disable the write operation using this instruction. Okay, now read status register, that is RDSR, it will provide the bit information, like which bits are set, which bits are disabled. Okay, so we can see that in the status register, first bit number 7 is WPEN, that is WPEN. So meaning of this, like it is already mentioned over here, we will go through it one by one. Write protect enable, that is WPEN. Okay, then bit number 5, 6 and 5, these are unused bits. Now bit number 4, 3, 2, these bits, these are the block protect bits, BP2 to BP0. Okay, these are the block protect bits. As we have seen, like we can configure various bits, right? There are like basically four states or five states, right? 1/8 sector 1/8 of like sector number 8 will be block protected. 1/4 memory array will be block protected. 1/2 memory array will be block protected, and all memory will be block protected. So these four settings we can do, or we can disable like block protect. So total these four plus one, there will be the five settings. So using these 3 bits we can set the block protect. Okay, so bit number 4 3 2, bit number 2 to bit number 4, these are the block protects. Bit number 1 is write enable, and bit number 0, this is the ready state. Okay, it is active low. So bit number 0, it is a ready state. Okay, whenever this bit is 0, it indicates that device is ready. Whenever this bit is 1, it indicates that write cycle is in progress. So we can use, for efficient programming we can use this bit. Okay, but in our code we have not used this bit, so we will modify that our code later on when we develop the professional applications. Okay, now bit number 1, this is the write enable. Bit 1 0, if the bit 1, that is if it is equals to 0, it indicates that device is not write enabled. Okay, bit 1, when it is 1, it indicates that device is write enabled. So we can again check this the bit whether the device is write enabled properly or not. Okay, whenever we are sending the write enable instruction. Now bit 2 BP0, right? BP0 to BP4, these are the block protect bits. We will see this into this table number 4. Okay, bit 5 and bit 6 are unused, and bit 7 is again write enable operation. Okay, now we will check product ID. So for our IC we will get 1FH, 1F, right? So whenever we are sending the 1F, we will get the device code as 64H. 64H, yes, 64H. So basically we will get 2 bytes of data. First will be 1F, second will be 64H. Okay, so first byte after the instruction will be 1F followed by 64H. Now write status register, like we can use the write, like these bits, we can use the block protect bits, we can write the status register to enable these bits. Okay, yeah, so I am improving on my explanation day by day. So if there is any explanation that you think is missing, you can write it into the comment section. If I miss any point, then yeah, you can write it in the comment section. I will try to get it covered in the next video. Okay, so we have seen like most of the commands. Now we will go over here and we will see like how the communication happens. Okay, basically, so synchronous data timing, we are using SPI mode 0, that is clock polarity is 0 and clock phase is 0. Clock polarity 0 means whenever the chip select is going from high to low, or there is a transaction going on high to low, or we are enabling the device, so the clock polarity of clock, that will be 0. Okay, that will be clock polarity will be low. So this is CPOL 0. Now clock phase 0. Okay, clock phase 0 means data will be sampled over here. So you can see that whenever the first transaction on the clock polarity, clock pin, okay, from low to high, so data must be valid. Okay, and it will be shifted. Okay, so here data can change, basically here data can change. Okay, so data must be valid whenever the clock is going from low to high. For SPI mode I am talking. Okay, so we can see high state and low state. We can see that data is transaction over here. Okay, when the clock is low, data is transaction is over here. Okay, on the SI line. Same goes with the SO line. Whenever data clock is low, the data will change whenever the clock is low. Okay. Now write enable timing. So we have seen that before every instruction we have to write the write enable instruction. Okay. So write enable, the chip select is going from high to low, device is enabled. The clock is low when the chip goes from high to low. Okay. Then we have to send the write enable opcode. We have seen that we have to send the MSB first. Okay. Then write enable, for write enable we have to send 0x06, right? So we'll go over here, we'll go into SPI Flash. Okay. Device ID. So this one practice I'm following, that we are creating the libraries. Okay. So opcode for write enable is 0x06. Okay. We have seen, I'll match every opcode over here, or you can see the opcodes over here, right? So I'll bring it over here and yes. So for write enable we have 0x06. For write disable we have 0x04. For read status register we have 0x05. For write status register we have 0x01. For read we have 0x03. For write we have 0x02. For sector erase we have 0x52. We have 0x52. For chip erase we have 62. And for read device ID we have 15, right? For read device ID we have 15. Okay. So these opcodes, these are matching over here. Okay. I will go which pins are used for what purpose and everything. Okay. So basically, okay, we'll go in our code directly. So we will see that the pin number 3, right? Pin number 3, GPIO pin 3, it is selected as chip select. Okay. So GPIO pin 3 of port A is selected as chip select. We have connected it as chip select. Okay. Write protect and hold pin, we are not currently, these two pins are unused. Okay. So slave in, if we see slave in, it is connected to PA1. Okay. So slave in PA1, slave out PA2, and clock is connected to 0. Slave out is PA2 and clock is connected to GPIO 0. Okay. Now these are pin ports. Okay. So all pin ports are GPIO A. Now as we have seen, we have 256 bytes per page, right? The number of sectors are 8 and sector size is 65536, that is 64 KB. Okay. Now if we want to write block protect level 0x00, okay, we'll go into this code again. So there are total 5 levels, 0, 1, 2, 3, 4. Okay. So if you want to disable the block protect, we have to set it as 0x000. So in the write status register we have to set this BP2 to BP0, that is bit number 432 as 0000. Basically we will go into the code, so we can see that 0x00. For block protect level 1, 2, 3, 4 we have defined all these things. Okay. So we can see that for level 1, 001. Okay. So this is bit number 2, right? Means it will be 00. So it will be 0x00, sorry, 0x00 0x04, right? So we can see that 0x04, because this bit BP0 is bit number 2. Okay, now for level 2 we have to set the BP1, so it will be 0x08, 0x08. Okay, for level 3rd we have to set 11, that is bit number 3, bit number 2 we have to set it to 11. Okay, so it will constitute 1100, that is C, so 0x0C. And for all protect bits, like we can consider it as 00. So BP2, this is bit number 4, so 0001 and 0000, so it will be 10, so it will be 10. So I have written the explanation over here, that is locked out sector is, that is the sector number 8 is locked out. Okay, for level 1. For level 0 there are no sectors are write protected. For level 2 sector number 7 and 8 are write protected. For level 3 sector number 5 to 8, 5, 6, 7, 8 are write protected. For level 4 sector number 1 to 8 are write protected, means all sectors are write protected. Okay, so like these are the macros defined. Okay, now we will go into the write enable instruction. We will see first see write enable and write disable instruction. Okay, so like we have used one uint8 because the data that we want to set is an 8-bit, that is word, right, one word of data. So we have assigned tx data is as opcode write enable opcode is assigned to tx data, this variable. Now chip select, in the chip select we are like transaction from high to low on the CS pin. Okay, so write enable port, CS pin port, the pin and the reset, means high to low transaction. Okay, and there is a delay of 5. Okay, so we have customized this delay. Basically if you go into the delay function, we have customized this delay. Somewhere here we have customized this delay, somewhere here we have customized that delay. So basically that delay is of 4 to 5. Okay, yeah, so here it goes, delay count is 5. So for 5 times we will there is no operation instruction, so we will waste, basically we will waste 5 instructions over here. Okay, in the chip select. Okay, now we'll go back over here. Yes, write enable. So like we have made the chip select as low. First thing first, we have made the chip select low. Okay, for write enable we have made the chip select low. Okay, then the send the data. Now what data we have to send? We have to send the write enable opcode. We have to send the write enable opcode, which is 0x06. So we have sent the data. Okay, so data, and then we have to disable the chip select. Now we have to disable the chip select. Now we will go into this send data function. Okay, so remember first we have to send the MSB first. Okay, now we have used the one pointer. We are using two arguments, one is pointer, one is data length. Okay, so we will be using this function for multiple operations, that's why we have written in this fashion. Okay, now data bit, okay, and data shift bit. Okay, so basically we have entered it as 80. We want to send the MSB first, that's why we have made it like 80. Okay, so for loop count, that is uint32, because we have like 512 kilobytes of data, so that's why we are using it, we are assigning this variable as uint32. So starting from 0, loop count starting from 0 until we reach the data length, that is all data has been transferred, either single byte of data or multiple byte of data. So for write enable instruction, as you can see, for write enable instruction we want to send only 1 byte of data, that's why we have written 1 byte of data. Okay, first thing. Okay, now coming over here, so data length for write instruction is of 1 byte. Okay, now loop count. Now data shift, coming inside this for loop, data shift is assigned to 80. Okay, now for loop we are again like rotating this for 8 times. Like why 8 times? Because we want to send each bit. So in serial communication, a bit like we are sending bit by bit. We don't send 8 bits simultaneously or parallelly. We send first bit, after that in the next clock cycle we send the second bit. Okay, so likewise for this serial communication we have used this for loop. So we will be sending the data or we will be rotating this for loop for 8 times. Okay, now we will be sending one bit of data at a time in one clock cycle. Okay, so 80. Now whatever the data is there, we are ending with the data shift bit. Okay, that is 80. It means the MSB. Okay, now data bit is shifted by 7 minus loop. So this is the loop count is equals to 0 in the first iteration, right? So 7 minus 0 will be 7. Data bit is shifted 7 times. We can write it as like this, or we can basically write it as like if the data bit is equals to 1, means after ending this, right, if the data bit is equals to 1 means the first bit it is 1 or it will be 0. So depending on that we can do like this, or we can shift the bits. Okay, so I have used the approach as shifting approach I have used. Okay, rather than the else if approach. Now depending on the bit, right, now the MSB it will come to LSB after shifting it 7 times, right? So it will come over here, it will be set or reset, it will be sent. Now like we are sending the data bit over the slave in, master out, slave in. So GPIO port, pin, slave in pin, and the bit, whatever is the state of the pin, either 1 or 0. Okay, after that we are providing the clock. Now we'll go. Okay, after that we are providing the clock, and we are shifting this data shift bit, right, means this data we are shifting it by 1. Okay, so 80 will come to as 40 in second iteration. Okay, so second bit will be shifted, that is bit number 6. Okay, after again like coming to next iteration, bit number 5 will be sent. Coming to next iteration, bit number 4 will be sent. Coming to next instruction, bit number 3 likewise it will be sent. Okay, so we will come in like after coming over here we will increment the pointer. So it is a byte pointer, we will increment the byte pointer. Okay, we will increment the byte pointer and we will come outside the for loop. We will check if the loop count is greater than the data length. Now for a write enable instruction, the data length is of 1 byte. Okay, so the loop count is equals to data length, so it will directly come out of the for loop. Thus we will send the first write enable instruction. Okay, now we will go into the clock. So basically like we are setting the clock and we are resetting the clock. Why we write like the clock pin set first and reset first? Because we are using the SPI mode 0. So the initial polarity of the clock when the chip select goes from high to low, it will be low. Okay, so the first transaction will be from high to low. So that's why we are setting it first and then we are resetting it first, resetting it later after some delay. Okay, so this is the send operation. Okay, this is write enable instruction. So yeah, so coming over here, this is a write enable instruction. Similar to write enable instruction, there is a write disable instruction. Instead of this write enable opcode, we are using it as a write disable opcode. The rest of the functionality is same. Like we are enabling the chip select, that is we are from high to low transaction on the CS pin. Then we are sending the 8 bits starting from MSB to LSB over the SI line. Okay, then we are disabling the chip select, that is from low to high on the CS pin. Okay, again we will go into send data. So I'll once again explain this. Whatever the data bit, okay, this data bit, okay, we have used over it here because we want to send a single bit, and we don't want to hamper the data, the actual data at that time. Okay, so data bit we are taking the single bit at a time. Okay, so to take the single bit, like we are basically taking it as 80, okay, ending it with 80. Take like this is the extra caution basically. Okay, ending it, getting the MSB, assigning it to over here. Okay, bringing the MSB to LSB and sending it over here. Okay, data bit. Then again coming to the bit number 6 in iteration 2. Okay, sending the bit number 6, bit number 5, bit number 4, likewise, and in the last iteration we will send the LSB, that is bit number 0. Okay, so in this way we won't hamper the data, that is write enable instruction. Okay, so write enable, write disable. Okay, write enable and write disable. So write enable, write disable. Then we'll go for program timing because we want to, okay, we'll go for sector erase first. Sector erase. We'll go for sector erase, right? So before every instruction, we have seen in the datasheet that before every instruction we have to send the write enable instruction. Okay, so we'll go into sector erase. Okay, so we got the sector erase opcode that is defined in this. Okay, .h file, sector erase, right, .h file. Okay, now memory address is of 3 bytes. So sector erase, which sector do we want to erase, so that memory address we will need. Okay, so for sector erase we will be needing the memory address. Okay, so uint 8, because we are sending the bit by bit, right? So basically we have constitute this into 3 bytes. Okay, so this uint 8 we will constitute it into 3 bytes because our memory length is of 24 bytes at max. So our memory length, that the maximum address length is of 24 bits at max. Okay, so that's why we have converted this uint32 into 888, that is 24 bits. Okay, then the memory address, so starting from the memory address 0. Okay, we have given the pointer. Now memory address, we want to convert this memory address, 24-bit memory address, into byte. We are chunkatizing it basically. So memory address is shifted by 16 and ended with FF. Okay, so thus we will get the first from bit number 23 to bit number 17 we will get. Okay, so this will be stored into memory address 0. Then next 8 bits, that is from bit number 16 or bit number 15 to bit number 8, it will be stored in memory address 1. Okay, in this array, and like last 8 bits will be stored over here. Okay, so if we see, that is 3-byte address, bit number 23 to 22 likewise. So first we have to send from bit number bit number 23 to bit number 16, right? From bit number 5 to bit number 8, from bit number 7 to bit number 0, likewise we have to send. That's why this shifting and ending operation has been done. Okay, now before sending any instruction, again I am repeating this will be kind of boring to you, but this is very much important to send the write enable instruction before every instruction. Okay, so write enable instruction, then we are sending the chip select, then we are sending the data. Now this data, what this data means, we are sending the instruction. Okay, so first instruction is sent, right? First instruction is sent, 1 byte of data we are sending the instruction, 1 byte of instruction. Then we are sending the memory address, right? It is 3 byte of data. then we are sending the memory address which is of 3 bytes, right? Then we are disabling the chip select, and then we are giving some delay. Okay, so if you can see, first we are sending the instruction, then we are sending the 3 byte of data. Okay, then the halt delay. Now we can see that we have given the 50 microseconds of delay. So again, I'll go to the timings. I'll show you the timings why we are using this much number of delay. Okay, now yeah, now for this chip erase, we will go for chip erase. So chip erase is simple. Before sending any instruction, we are sending the write enable, then we are setting the chip select, then we are sending the data, that is 1 byte of data. As you can see, for chip erase we need only 1 byte of data. We don't need any address after this instruction. Okay, so chip erase will erase the whole chip, and then we are giving the 8 second of delay. After disabling the chip select, we are giving the 8 second of delay because it is needed and it is mentioned in the datasheet. I'll show it to you. Okay, now opcode for chip select, sorry, opcode for chip erase, that we have set it over here. Okay, so 0x01100010. So this is 6-2, right? 6-2, that is 6-2. So opcode for chip erase is 6-2. Okay, so likewise now, okay, so we have seen chip erase, we have seen the sector erase. Now we want to see how we can write the memory data. Okay, mem data. So for to write the mem data, we will needing the 3 arguments. First will be the memory address, second will be the byte pointer to the data, and third will be the data length. So how much bytes of data we want to write. Okay, again it is same. So if you go for the program, right, program, first we will be sending the instruction, second we will be sending the 3 byte of 3 byte address, and third, after this 3 bytes of address, means after sending 24 plus 8, after sending the 32 bit 32 clock cycles, we will be sending the actual data. Okay, over the SI. So we got the opcode. First we will send the opcode first. Okay, then after that we will send the address. Okay, and then we will send the data. So when the data length is not equals to 0, so basically this data length is not equals to 0, we'll check. Now again, like this is the some logic that we have written to prevent from page byte write. Okay, page overwriting. So we can write only 256 bytes in like in one instruction, write instruction or program instruction. So after writing 12, or if we are writing at the page boundary, then we have to send the instruction, then the new address, and the rest of the data. So likewise we have to send. Okay, so basically this provision is for that. So if the data length is greater than the bytes per page, that is 256 bytes, what we will be doing is data bytes to write will be set to 256, then the data length will be reduced by 256 directly. Else what we will do is, if the data to write is less than 256 bytes, we will be directly given data bytes to write is as whatever the data is, and we will directly reduce it the data length to 0. Okay, now the same logic for the memory. We will shift first to get the bit number, shifting and ending to get bits, address bits from 23 to 16. Okay, so this is done to get the address bits from bit number 16 to 23. Now this is for 15 to 8, and this is for 7 to 0. Okay, 7 to 0. So we are shifting it from 16 to like we are shifting it from 16, ending it with 0, 0x00. So thus we will get the byte like from 23 to 16, and then from 15 to 18 shifting it by 8. Okay, and then directly ending with 0xff. So we will get this lower 8 bits. Okay, so again, before sending any data, so before sending any new instruction, we are sending the write enable instruction, then chip enable. Okay, chip enable, then send data. So we are sending the instruction first, that is a single byte instruction. Then we are sending the address, that is 3 bytes address, and then we are sending the data, actual data that we want to write. So we are providing the pointer, send data is a pointer, and bytes to write. So how many bytes we want to write. Okay, then we are disabling the chip select. Then we are giving some delay, hard delay of 100 microseconds. Okay, now once we once we write 256 bytes. Okay, if we are writing at the page boundary, or if we are writing at 256 bytes from 00000, okay, so that will be taken care over here. So it will be taken like the memory address. If the data is greater than 256 bytes, then the memory should be incremented by 256. So that is taken care over here, that is we are incrementing the memory address by 256 bytes. Okay, and the pointer to the data is also incremented by the 256. So writing first 256, then getting the new data after 256 bytes, and so the pointer is incremented basically from 256. Okay, so likewise we are doing this. So if the data length is greater than the page size, that is 256 bytes, 256 bytes. Okay, bytes. Write the first page size bytes, that is 250. Write first 256 bytes, then increment the memory address by 256. Okay, then write the next page bytes, that is write next 256 bytes until remaining bytes are equals to 0. Okay, so this way we are writing the memory data. Now we have seen which topics we have covered is till now is we have covered the SPI communication. Okay, so serial peripheral interface, SPI modes, mode 0, mode 1, mode 2, mode 3, depending on the clock polarity, clock phase. Okay, so for our device we are using mode 0, SPI mode 0, clock is 0, polarity is 0. Clock 0 means whenever chip select, there is a transaction on chip select pin from high to low, the clock pin will be always low. Okay, so whenever there is transaction on chip select pin, the clock will be always low. That means clock polarity 0. Clock phase 0 means the data will be sampled on the first edge, that is for our SPI mode 0, that is a rising edge of the clock. So data will be sampled at the rising edge of the clock. Okay, so our device operates on SPI mode 0. Okay, now in the device datasheets, how many bits? There are total 4 megabits, that is 512 kilobits. 512 kilobytes of data. Okay, so we have seen the write cycle, we have seen the device opcodes basically first, then we have seen the write enable cycle. Okay, then chip erase, sector erase. Okay, this we will cover in the next video. The write operation and write enable instruction must be set before each instruction is sent. Okay, then we have seen the sector protect, that is block protect or sector protect. Block protect or sector protect. So before sending any instruction, we need to send the write enable instruction. Okay, we have seen the opcodes also. Now coming back to our main code. Okay, device ID, we have currently we have not written anything for this device ID. Okay, we have write this array, data array. So I'll modify this data array to quickly show you that our code is working. Okay, yes, simulation basically. Okay, Yes, this data we will be writing it in our memory. Okay, so data size is size of the array. Basically it calculates at the compilation. Then we have declared one array for reading the data and status register value. Okay, so these two variables, as we go on as we go through our code, we will see how why we have declared these variables. Okay, these variables or this array basically. So this is the general initialization of our code that STM32 IDE provides. Okay, the user code begins over here. First we have used the chip erase. That is not necessary, but for our simulation purpose I'm using this chip erase, or we can directly use sector erase. Okay, so one more thing, in the serial flash, if at particular memory location, if the data is not FF, okay, so we cannot write a new data over there. So that we have to take care each time. If we want to write a new data, first we have to ensure that there is no data. Okay, no data is in sense there is FF written. If something else than FF is written, that means the data is present over there, and we cannot write the new data on that particular memory location. Okay, so for that we are using chip erase. Then we are writing the data at memory location 0x00. Okay, so I'll change this as from 80 for our simulation purpose. Now we'll be writing at after writing the data memory, we are erasing this data, erasing the sector erase. Now this address 10, right, 100, this comes under first sector. Okay, because one sector constituted of 65536 bytes, that is 64 KB of data. Okay, so this comes under sector 0, so our sector 0 will be erased. Okay, that is automatically taken care by the device. Irrespective which memory location that you provide, it automatically decide which sector it has to erase. Okay, and then we are giving a 5 second of delay. Then again we are writing the data at 80 location. We will modify this, we will write it at 80 location. Okay, so we have built our code. As you can see, I'll scroll down to the end of the program, end of the main file. So we have not added any additional function over here, so that I can fool you. We are not doing like that. Okay, now we'll go in the simulation. You can see 1056. Okay, I'll load the latest hex file, 1055, 1056. That's the same. 11th 8th. Okay, open. Now we are writing the data at 80 location. Okay, we'll remember that. Now see the chip erase, right? After sending the chip erase, this is the write enable instruction. You can see that 0 0 0 0 0 1 1 0, that is 0x06, right? You can see that 0x06, that is for the write enable. So before sending the chip erase, we are sending the write enable. Now 0 1, okay, 1 and 0. So 6 0 0 1 0, 6 2, right? 6 2 is for chip erase. So thus we are sending the instruction. Even after sending the chip erase, right, if you can see 1 2 3 4, okay, you can see like only this many data has been erased. So basically chip erase takes some time. Okay, now we will go over in our code, we'll check the timings. So there it is mentioned that chip erase instructions take around 8 seconds or 5 seconds, I guess. Basically chip erase. We enlarge this. Yes. So erase cycle time per sector, it is of 1 second. Okay. And chip erase, right, byte program cycle erase cycle per time per sector. Total, there are total 8 sectors, that's why I have mentioned it as 8 seconds. Okay. So yes, that's how we have written, that is 8 seconds. Now you can see that from 80 location our data, that is STM Metatronics in embedded simulation, that we have written. Okay. So this is the write operation, that is we are writing at the particular memory location. So after 5 seconds this will be erased, that because we are writing the sector erase operation. So yep. Also sector erase takes some time, so you can see at memory we have earlier we have written data at memory location 80, so there is no data now. Okay. So yes, likewise we can see. Okay, where it goes, yep. Write instruction 0 0 0 0 0 1 1 0, that is 0x06, this is the write enable instruction. Okay. Then 0 0 0 0 0 0 1 0 means 0x02, right, 0x02, that is write instruction. After sending the write instruction, right, 0x02, we are sending the data 0 0 0 0 0 0 0 0, this is first 0. Okay. So if we see our memory address is 0 0 0 0 80. Okay. So next 8 cycle there will be, it will be low, again low. Okay. So this will be, bring it over here, 0 1 2 3 4 5 6 7 8. Okay. Now in the next 8 cycle we can see that 1 0 0 0 0 0 0 0. So in the next 8 cycles we are sending the 80, so 0 0 0 0 0 80. So this is 3 bytes of data, and after that we are sending our data. This is the actual data, that is STM Metatronics in embedded system. So first instruction, then 3 byte of address, and then actual data. Okay. This is with the write enable. Yep. Now again this is 0x06, that is write enable instruction for sector erase. 0 1 0 1, that is 5 0 0 1 0, right. So from here to here it is 5 2, right, sector erase. So 5 2, that is sector erase. Now the memory address that we want to erase basically. So 0 1 2 3 4 5 6 7 8. Okay. Then again 1 2 3 4 5 6 7 8, and then 1 2 3 4 5 6 7 8. Okay. So we have sent the for sector erase, right, for sector erase we have sent 1 0 0, right, for sector erase 0 0 0 1 0 0. Okay. So 1 0 0. Okay, like we have sent. So yes, hope you understand this explanation. If you have any doubt, you can post it into comment section. I will resolve your queries, I will resolve your doubts, and in our next video we will see how we can read from the memory. Okay. So we will be checking rest of the functions, that is device ID, memory read operation, write status register, read status registers. All these operations we will check in the next video. So I hope you like my video. If you like my video, share it, subscribe my channel, and thanks for watching the video. Have a good night.